Everyone, and welcome to the Cryosphere Pavilion. My name is Christina, and I'm a geophysicist at the University of British Columbia in Vancouver, and I'm part of the Early Career Scientist program here at the Pavilion. And I have the pleasure to introduce our next session, which is called The Need for Preventive CDR to Limit Long-Term Cryosphere Risks. We will have 4 speakers. The first speaker will be Karl Friedrich Schleuser from IIASA, the International Institute for Applied Systems Analysis in Vienna, who is here with us in Baku. And then online will be joining us Ute Klemme from Climate Analytics, Nico Bauer from PIC, the Potsdam Institute for Climate Impact Research, and Ruben Witt from Humboldt University in Berlin. So they will present 2 projects for carbon dioxide removal in the cryosphere, and this is really important to learn about these different measures, especially in the light of current rising CO2 levels and current NDCs. So I'm really excited for the next presentation. Thank you.
Yeah, thank you, Christina, and apologies for the technical glitches. We are still not really out of the woods. But we'll see how we manage. Okay, so I'll start introducing a little bit the Provide project and also give us a bit of a rationale of why we are talking actually about overshooting carbon dioxide removal in the context of the cryosphere at all, because that's maybe first an important starting point to establish. So first, we are actually having a joint session of 2 EU Horizon projects. That's projects by the European Union that are consortia projects of multiple research institutes focusing on cutting-edge research questions. In this case, basically, in particular, around the context of carbon dioxide removal. Okay, even more. Okay, exactly. All right, good. So the first project that I'm presenting is the Provide project, which is explicitly focusing on the consequences of potential overshoots of the Paris Agreement 1.5 limit and what it would mean for a range of systems, including the cryosphere. All of our results you can actually explore on the Provide Climate Risk Dashboard that you see here, and you can scan that QR code to browse through it. This also includes very detailed information on cryosphere risks, including northern peatland and permafrost loss, as well as glacier loss. What we're doing is we explore a wide range of scenarios and then project them into different sectoral risks, all the way even to an urban risk level, but also, and soon to be explored on the dashboard, even to the level of individual glaciers and the consequences of overshoot for them. We do so for a range of timely scenarios, including from the latest IPCC Level 3 assessment that allows us to tie our assessments a bit more closely to policy relevant targets. We can actually compare projections for where the world would be headed if current policies were not improved, compared to what can still be avoided if the world was to pursue a 1.5 degree pathway. We then look into a range of different subsystems, spatially explicit, so you can explore impacts by region and by country. And we do so in particular with a focus on trying to map out what risks of climate change are actually already unavoidable, even in the most optimistic mitigation scenarios that we can assess, and what risks of climate change are still very much avoidable by actually pursuing such a scenario compared to where we're currently headed. And it looks a bit like this graph there at the bottom, so you can look at different extremes, also cryosphere risks, and explore what the benefits of synergy mitigation are and how they play out over time. So why are we discussing this in the context of the cryosphere? The first thing is because overshoot comes with irreversible risks, in particular for a range of cryosphere systems. This is a recent study that we published. It looks into precisely a question, and here we show results for future sea level rise in 2300, as well as results for heat and permafrost loss here converted into an additional increase in global temperature. And you do see that 100 years of overshoot are causing about 40 centimeters of sea level rise in the best estimates in 2300, and we do see significant additional warming because of heat and permafrost losses. These are irreversible. This is a legacy of overshoot. and we need to consider them very carefully. In particular, also when you look at the high-risk estimates. So when we were to see much stronger responses of those systems across irreversible thresholds, including, for example, for ice sheets, we may see up to 1.2 meters of sea level rise for 100 years of overshoot. So a very, very significant commitment potentially arising from overshoot pathways. That's not the only thing we want to be concerned about when we talk about this, but obviously we would very much want to consider the risks for crossing irreversible thresholds for certain tipping points of the climate system. And that's another study that we published this summer, looking into the questions of what does overshoot and different levels of peak warming mean for the risks of actually exceeding or triggering tipping points. And you do see that, in particular, if peak warming was to exceed 2 degrees, the risks of triggering at least one of the tipping points of the climate system increase very, very strongly. On the current trajectory where we are on, if we were to head to 3 degrees by the end of the century, we have a more than 50% chance of actually triggering at least one of the tipping elements of the climate system. But then also, even if we were to overshoot the 1.5 degree limits, what's the point then in the long term of an overshoot at all if it comes to irreversible consequences? And the point is, it's still a lot better than actually staying where you ended up. So even if you were to exceed it, and you would need to live with the irreversible consequences of it, staying there and not going back down into a long-term temperature drawdown would be the worst option. We also quantified this a little bit, and here you see this again, kind of the plot that I showed before. This is now the benefits of actually pursuing a long-term temperature decline under achieving net zero greenhouse gas emissions as by the Paris Agreement, compared to stabilization at net zero CO2. What you do see again is you could avoid about 0.5 meter of sea level rise by actually bringing temperatures back down again in the long run. And for the high-end risk, this could be as much as 1.5 meters. So that's really something that is relevant and can avoid still the legacy of climate risks in the very long run, even in cases where we are achieving too high peak warming levels. But we really want to do this potentially in all cases, even if we manage to peak warming around 1.5 degrees. That's not a safe place to stay either. We really, in the very long run, need to go more closer to 1 degree or even lower than that to actually limit long-term climate legacy risks. The same is true for crossing potential tipping points. So this is again kind of the same risk graph, but now delineating between pathways that achieve net zero greenhouse gases as by the Paris Agreement, and therefore limits the long-term risks of potentially triggering irreversible tipping points compared to the pathways that don't. So you go from left to right, and you very clearly see, okay, if you are in a world where you don't achieve net zero greenhouse gases and you don't maintain it, the risks of actually triggering tipping points in the long run increase very drastically. So with that motivation, or why we're actually even talking about this, I hand over to my colleague Uta and give the context that she's going to explain a bit now what is actually required to bring temperatures back down in the long run, and what it would mean in terms of scenario and technology assumptions. And it's something that in particular the rescue project has explored in great detail. So Uta, over to you.
Thank you very much, Carl, and I hope you can hear me. If you could just maybe quickly signal if you can hear me well or not.
We are all huddling around the speaker, so okay. It's okay.
That's good. In true COP fashion, you're huddling. Very good. So yes, I will start. And yeah, let me know if you can't hear me well. So yeah, hello everyone, and thank you very much for the opportunity to present at the event today. And I'm sorry I can't be there in person. My name is Uta Klönne. I'm a senior science advisor at Climate Analytics and a project member of the Rescue Project. And in the next few minutes, Nico Bauer, also from the Rescue Project, and the Potsdam Institute for Climate Impact Research will present some of the work of the Rescue Project in the CDR space, as Carl has indicated. So yeah, first of all, the rationale of the project is that the deployment of CDR is unavoidable if net zero CO2 or greenhouse gas emissions are to be achieved. This is, of course, a central finding from the recent IPCC Working Group 3 contribution to the 6th assessment report. And the report also states that CDR methods vary in terms of a range of factors: maturity, removal process, timescale of carbon storage, and the CDR methods also vary in terms of their impacts, risks, and co-benefits of CDR deployment for ecosystems, biodiversity, and people. So this as a bit of a starting point. And this is also kind of the starting point for the Rescue Project, which develops new CDR portfolio scenarios for this century and beyond to analyze the response of the Earth system to different trajectories with or without overshoot. And then secondly, based on these new scenarios, Rescue assesses the potential role of CDR in reducing net greenhouse gas emissions, as well as its environmental impacts, side effects, and potential co-benefits. And so, yeah, this work is coordinated by the Barcelona Supercomputing Center, BSC, with overall 17 partners, and the project is now around half-time with an overall runtime of 4 years. So yeah, we would now like to present some of the preliminary results from the project, which we have just published in a policy brief on the role of carbon dioxide removal in 1.5 scenarios with and without overshoot. And you can download this via the QR code or also on the Rescue website at rescue-climate.eu. And the policy brief is based on preliminary results, which is work led by Leon Merford and Nico Bauer at PIC. And with that, I would like to hand it over to Nico, and maybe you can also test if people can hear you well.
So do you hear me? Is it okay?
Yes.
Good sound? Okay. So in the rescue project, we use an integrated assessment model, the Remind MACPI model, to assess the importance of CDR options in mitigation pathways until 2100. We look for 4 CDR options in particular. So one is afforestation, reforestation, bioenergy with carbon capture and storage, direct air capture and storage, and ocean alkalinity enhancement. So a really broad portfolio of different options. We can also add more, but in the rescue project, we focus on these 4. With the integrated assessment model, we apply then different budgets, carbon budgets over the 21st century for the 1.5 degree target, or the non-exceedance probability of 1.5 degree is 50%. And this leaves us with 500 gigatons of CO2 from 2020 onwards. And for the 2 degree target with a non-exceedance probability of 67%, this is 1150 gigatons. Okay, since 2020, we have had further emissions that have shrunk the budget, but we start these computations now from 2020 onwards. And in the no low overshoot scenarios, the budgets cannot be overshot, but in the high overshoot scenarios, and this is a temporary overshoot, so we exceed the budget, but then we decline and reach the budget up until 2100 again, and this via the large-scale application of CDR. So next slide, please. Here you see basically the results. In the top row, the middle figure shows the cumulative emissions, and there you can clearly see that the 1.5 degree and the 2 degrees scenarios can have very different pathways with cumulative emissions, but end up with the same level in 2100. This also reverses global mean temperature by 2100, as you can see in the top row right. The annual emission pathways are very, very different. So we are circling around 0 in the 1.5 degree with low overshoot, and go very, very strongly negative in the overshoot scenarios. The application of the CDR portfolios is very, very different. And the no and low overshoot scenarios, we basically have afforestation and BECCS. And when we don't allow for an overshoot, we have strong near-term application of CDR. In the long, if we allow for the overshoot, then we have cumulatively more CDR, but more in the long term. So it is a matter of scale and timing. And in the scenarios with overshoot, we also apply the DAX option and also the ocean alkalinity enhancement. And yeah, with this, I hand back to Uta again. Thank you very much for your attention.
Yes, thank you, Nico. Thank you for this. And yeah, now I would just like to go into a few further considerations to put the results into context. And one is that scaling up CDR comes with sustainability and feasibility constraints, which also kind of depends on the magnitude of overshoot, as Nico has alluded to. High overshoot pathways come with much higher climate risks and impacts compared to pathways with lower overshoot, including for the cryosphere. Carl has already spoken about this. And then going a bit more into the policy side of things, so CDR in different scenarios that limit warming to 1.5 is generally higher than the CDR proposed by countries. So this means that CDR would need to be ramped up in countries' NDCs as part of more ambitious 2030 and new and ambitious 2035 targets, which countries have to come forward with, of course, until early next year, which separate out CDR. And they also need to be implemented while addressing these feasibility and sustainability constraints. And so now I would move into also work done a bit under another project, because this last point of countries' plans and targets is kind of going into the question of who will deploy the CDR. And this is work done under the CDR Poet project. And the starting point here is that the required CDR to limit warming to 1.5 raises questions about what would be a fair allocation of CDR deployment by countries. And yeah, we have also just published a policy brief on this issue with the example of Germany, which you can download here as well. And so what we did is we looked at the example of Germany, that Germany emitted above 16 gigatons CO2 over an equal per capita basis between 1990 and 2023, and plans to emit a further 2.3 gigatons CO2 until Germany's climate neutrality goal in 2045. And this is what is considered Germany's historical and future carbon debt. But Germany's fair CDR contribution is much larger due to both its responsibilities as a historical emitter and also its capability to do more. And so we conclude that Germany should deploy 6.4 gigatons CO2 of CDR up until 2045 to align with the Paris Agreement's objectives. And this is significantly more than Germany's current plans. And so, yeah, to minimize Germany's future carbon debt and also CDR deployment, Germany must undertake, of course, more stringent emissions reduction efforts, which is a central finding as well. And yeah, if you want to go more into detail of this, you can download the policy brief here at the QR code or also on the CDR Terra website. Thank you very much for listening, and back over to you.
Ruben, I think it's over to you.
Yes, perfect.
Yeah.
Thank you.
Perfect. Thank you, Uta.
Excellent. I guess you can hear me?
Yeah.
Okay, perfect. So, yes, hello, my name is Ruben Prütz, and I'm a PhD student at Humboldt University of Berlin, and I'm a project member of the Provide project that Carl already mentioned. And here during this presentation, I want to give you an overview of carbon dioxide removal taxonomy on potential side effects, potential implications, which we developed under the Provide project. And let me start with this stylized or conceptual plot why carbon dioxide removal is needed. So as you will know already, by now it's quite clear that we will need some level of carbon dioxide removal. And carbon dioxide removal is required for various reasons. First of all, to speed up emission or lowering emissions to rapidly achieve net zero CO2. Then at net zero CO2, it is required to balance any remaining residual fossil emissions. And then in the second half of the century, it's potentially also required to achieve net negative emissions to return from a temporary temperature overshoot. And such an overshoot is becoming more and more likely in the context of ongoing delay in deep emission cuts. We also see this in many of the pathways that are also considered by the IPCC, pathways from the AR6 assessment cycle, especially in pathways which limit warming to less than 2 degrees, and ideally even 1.5 degrees of warming with no limited or high overshoot. And as you can see in this plot here, in many of these pathways, we would have to deploy CDR of more than 10 gigatons in the second half of the century. And now such high levels of CDR deployment, of course, raise the question whether such high levels are feasible, whether we can scale enough, but they also raise the question whether, or like what implications, what side effects, what constraints may be associated, as Uta also already highlighted. Now, moving on, if we look into the scientific literature on carbon dioxide removal, we see that there has been a rapid growth, actually an exponential growth in recent years. And on the one hand, this influx of research on carbon dioxide removal is a good thing because it helps us to synthesize or close remaining evidence gaps. But on the other hand, it also makes it increasingly challenging to track new developments and also to keep an overview to synthesize new evidence. And this is now where our mapping study under the PROVIDE project comes in. Because in this mapping study, we mapped the literature evidence on carbon dioxide removal side effects, just get a better understanding of what is already being researched in this regard, and also to identify further potential research gaps that we then need to fill. And in this mapping study, we focused on 6 different land-based CDR options, which you can see here in this plot on the horizontal axis. These options are afforestation and reforestation, then bioenergy in combination with carbon capture and storage, shortly BECCS. Then we also focused on biochar, on direct air capture with carbon capture and storage, enhanced weathering, and also soil carbon sequestration. So these are the 6 CDR options that we considered. In addition to these options, we also considered some more general option-unspecific deliberations about potential implications. And in the study, we then identified 18 overarching side effect categories, which you can see here on the vertical axis. And now when we look a bit at this plot, we can see how much literature is already available for the different options and for the different side effect categories. And just from looking at this plot, you can see that there's already quite some research on afforestation, BECCS, and biochar, so implications or side effects for these 3 options, while there's currently still much less evidence on the other options that we considered. So on DACs, enhanced weathering, and soil carbon sequestration. In the study, we then also try to better understand how, the current research on some co-benefits, because some of the options may actually also have co-benefits, and some of the more negative side effects, which are exemplified here or highlighted in color. And again, from looking at the plot, we can see that there's a current predominance, or the evidence is predominated by negative effects, but at least for some options, for example, biochar or soil carbon sequestration, we also see some co-benefits associated with their deployment. However, I think here it is very important to reflect that this is not a real-world reflection of co-benefits and side effects, but this is just sort of a snapshot of what is being discussed in the literature as of now, and this may evolve as new evidence arises. Also, we have to consider that different studies that we considered are taking place in very different contexts, different deployment scales, different CDR option setups. So I think the main learning from this exercise is that the side effects are very context dependent, very setup dependent, and there are definitely negative side effects, but if we better understand how to minimize them, we can actually try to work towards increasing the potential co-benefits. However, this has limits, and I will come back to this later, but before I do, I want to highlight that in the study, we also looked into how the evidence on side effects, the current evidence on carbon dioxide removal side effects, is distributed geographically. And here we can see that there is so far relatively little evidence on potential side effects or implications of CDR in African countries and in South America. And this is quite interesting because these continents, these regions are actually deemed quite crucial, at least in the current mitigation pathways that we have, because in these regions, according to the pathways, we would have lots of land-intensive carbon dioxide removal, such as, for example, afforestation or BECCS. So this points to a potential literature gap because we first have to better understand the side effects before we then can get serious about deploying in these regions. Then I also want to highlight that in the study, we identified almost 400 individual effects, different side effect categories, which we then systematically grouped and categorized into a taxonomy. As you can see in this plot, it's very small, but that doesn't matter. I don't want you to go much more into detail, this is just to highlight that this taxonomy gives a very condensed overview of potential side effects and implications, and it also allows to compare the effect profiles of the different CDR options. And so, as this is a bit too dense for this presentation, we can actually aggregate the information a bit more and look into different dimensions of potential overconfidence regarding carbon dioxide removal, or potential dimensions leading to constraints. And so here we present 5 different dimensions that are very important in this context. The first one is readiness. And from recent evidence, we can clearly see that already now there's a gap, CDR deployment gap arising, because current levels are far away from what would be needed by mid-century in Paris-aligned mitigation pathways. This, of course, raises then the question again whether we can sufficiently scale in time to have enough carbon dioxide removal ready by the time we need it. And the next dimension of potential overconfidence is about permanence and resilience. And in this context, it's quite clear that durable CO2 storage is very key. And recent evidence shows us that, especially in the context of net zero targets, we need storage times of at least 1,000 years to effectively balance residual fossil emissions and to limit warming. However, some of the CDR options that we are often discussing, including afforestation and soil carbon sequestration, for example, these options are characterized by much lower storage timescales. And another important aspect regarding resilience is that in the context of ongoing climate change and increasing climate impacts, some of the carbon that we store in biomass and soils, for example, is also very vulnerable to reversal. For example, if you think about the increasing risk of forest fires or also droughts. So this is another potential dimension of overconfidence. Then there are also potential system feedbacks, which unintentionally may offset some of the removal or cooling benefit of carbon dioxide removal. And in this context, we think about albedo changes, for example, or also indirect land use change, which may trigger emissions in other places in the context of CDR deployment, which then in turn would offset some of the benefits that we would hope to get from carbon dioxide removal. Then the dimension, which is very important, is about policy response and governance. And here we know that from the sheer outlook of potential future CDR capacities may actually lower today's ambition to cut emissions. And this is quite dangerous because betting on future carbon dioxide removal capacity is a very risky strategy. Then the last dimension of potential constraints that I want to highlight is about sustainability aspects and acceptability. And as Uta already highlighted, and also myself in the context of this taxonomy, there are several implications which may threaten sustainability. They are very CDR option specific, but some of the overarching effects are, for example, high land demand, high water demand, high fertilizer demand. And at the scales that we require carbon dioxide removal, this may then also have negative consequences for biodiversity or food security. And in the light of these side effects, it's also clear that the public acceptability may actually be low, also when we consider aspects of burden sharing. And yeah, to wrap up this presentation, I think these 5 dimensions of potential overconfidence once more underline why it's so important to rapidly cut emissions in the near term to limit our reliance on carbon dioxide removal as much as possible. With that, I hand back to Carl, and I'm happy to answer any questions in the end.
Perfect. Thank you, Uta. Thank you, Nico. Thank you, Ruben. I'm gonna now if you think that this whole CDR thing is already really complicated and probably we shouldn't do it, I now want to make it even more complicated and convince you that you definitely need to do it. I will do so with the slides that are going to come in a second, hopefully. But ultimately, what we're going to talk about is something that we established as a concept in a recent study and call it preventive CDR. Because all the graphs, all the slides that we've been showing so far, and the stuff that we've been looking into, really has been focusing more on like what's our central estimates of warming outcomes. Can we basically bring warming back down again? What if we were to exceed 1.5 in the central estimate, and what would we need to do to get down? Ultimately, that's not the only possible future climate outcome that could be the consequence of our emissions. We could also very much see a world that sees much, much higher warming, both up to the time of the zero CO2, but potentially also beyond. And in such a scenario, we may actually require a lot more carbon dioxide removal than what we currently think. And now I need to sprint through all the slides again and go to the ones that I want to talk about. Here we go. So normally what you would see, or what we normally look at is scenarios like this. I go back one slide. And also how the IPCC report frames overshoot is very, very overconfident and precise in that regard. So you have a scenario and you say, okay, we're going to have a low overshoot scenario that's probably going to be an overshoot of about 0.1 degree, or in a high case, between 0.1 and 0.3 degrees. And this gives you very much the feeling, okay, we are in control of the global thermostat, and we can kind of reverse that, and we know what we are doing, and we can precisely even land again around 2100 at the warming outcome that we wanted. Unfortunately, that's not the full story. The full story looks more like this. All these plots are actually in different physically plausible outcomes, considering different feedbacks in the climate system and warming outcomes as a result. And you see that in the scenario that the best estimate would actually just be around 1.5 and not show any further warming. We cannot exclude warming outcomes of well above 2 degrees even, and continuous warming after net zero CO2. And if you think about this carefully, it means that there are much, much higher climate risks on the tail side than we normally consider, and we need to actually consider this in the context of also what are preventive measures we may need to take in case we are in such a scenario. So how would this look like? This is basically the same. Each of these plots is one physical climate outcome, and these are the same graphs and the plots that are on the left side. And you do see you can get a much higher warming at the time of peak warming, so that's around 2060 in this scenario. And you could actually get also considerable additional warming post 2060. So you kind of think you are net zero CO2, you've done it, and what you then see in terms of the climate feedback is, oh no, we could get additional warming until the end of the century of up to 0.2 degrees if we are unlucky. So obviously, it's not a climate resilient pathway if you actually don't plan for like not just worst case, but even like bad outcomes. So we need to consider this somehow in our pathway design and our reflections on policy. And if we did this, then this is now basically the required CDR that we may need to actually get back to 1.5 in such a scenario, compared to the full scenario uncertainty at the bottom. And what you do see is that basically the filled bar at the top, the geophysical uncertainty filled bar, that's a 1 in 4 chance, the 75th quantile, of the amount of CDR we would require to actually be in 2100 back to where we thought we were to in our best estimate. And this is comparable to the amount of CDR that's currently being deployed in the scenarios that we've just been talking about for the last half an hour. And it's just basically an additional dimension to the whole problem that so far we've talked about scenario uncertainty, we have talked about technology uncertainty, we have talked about the side effects. But if you then actually started looking into the geophysical uncertainties, you do see that this whole problem even is probably a lot bigger than how we currently frame it. Ultimately, what this would mean is we need to limit potentially CDR for any other applications than a preventive application with also the potential to draw down in the long run. And we need to scale it up at scale, despite some of the potential negative side effects that Ruben has been talking about. So if we consider all these things together, some things actually become quite clear that we currently not explore. Because right now, most of our emission scenarios either try to limit CDR and bring down residual emissions as much as possible, or they scale up CDR and give us some room for residual emissions in some sectors. And what we actually need to be in terms of the preventive capacities, we need to be somewhere in the bottom space. We need to bring emissions down as much as possible and in parallel scale up our capacity for carbon dioxide removal. And that is really basically that's the climate resilience strategy, unfortunately. So we need all of the above and then even more than what we've been so far discussing. And the only good thing I can leave you with at the end is that this is obviously a win-win, or like this is a no-regret strategy to do that. Because either we will be in the position to bring temperatures down again fast or faster, therefore limiting long-term cryosphere legacy risks that we've talked about in the beginning, or we are in a much better place in case we are look into a high warming world or high climate risk outcome, then we at least equipped future societies to actually deal with that in a comprehensive fashion and not squandered the opportunity to do something about it by using CDR technologies to actually just offset emissions rather than using them for temperature decline. So I appreciate it's been a bit of a ride through a lot of different aspects of a very complex topic, but I'm very much looking forward to a bit of a discussion. Apologies for the technical glitches in the beginning, but any questions to myself or also the speakers online, please do so. I appreciate we have a sound issue, so if you could come close to that mic, or if you want to ask a question, you probably try to pass it on so that that the people online can also hear you. And over to you, Christina. Thank you.
Are there any questions in the audience?
Yeah, any questions, comments?
I've not listened to everything, but I'd like to ask the question. So is it unmuted at the moment?
Yeah, I think they should be able to hear you. Yeah.
Okay, so
in
the last slide of the second last presenter, I've heard about the governance and resilience issues related to CDR. So my question is that in your paper, have you also considered the sustainability of CDR option in the sense that once net zero emission are achieved, then there is a chance for these heavy investment, especially the engineering option related to CDR to become, stranded assets. So have you looked at this dimension as well?
I think that's a very, very interesting question, actually, because I kind of, as another part of the technology side of this kind of, we are done reversing temperature and do a point landing, is that yes, you will build up an industry that at some point you would dismantle. So that is actually a question that I think is so far under study. We haven't looked at it, but I would also, maybe we can put the speakers on the screen, but also see if maybe from the rescue side, maybe Nico or also Ruben would have something to say about this. I think from our side, I would say there's clear merits in considering bringing temperatures down in the long run. So I wouldn't actually stop at net zero. Basically, you would at least enable future societies to make an informed decision of how low they would want to go. But I think ultimately the question of how do you phase out CDR again when you kind of don't want to do it anymore, I think is one that is also not yet comprehensively assessed. But I would look to other colleagues as well if they have something to add on that particular point. It's a very good question, I think. Yeah, Nico, please.
Okay, thank you very much. One question, could you mute on your side? Because we have very strong background noise. Thanks.
Okay, I'll try.
I think it is important to consider the stranded assets, but with respect to the CDR capital that we are building up, that is probably a thing that is, so to say, not so very immediate. Currently, it is very important to build up a reliable, robust investment environment to get first projects on the road. Yeah, to get the first investments really done, the pilot project phase and the first, so to say, pre-commercialization plants online, where we really can test and improve on the technologies to bring the investment costs down and to better understand the operation of these things. On the side of the regulations, I think it is very important with a perspective on a larger scale ramp up of the CDR capital, that we now need to make saving decisions and secure funding for this purpose. Yeah. the remediation of a environmental debt that we are building up requires that, on the other hand, you build up a financial capital, a budget that is earmarked with the purpose to remediate the natural capital. In our case, that would be to restore the carbon budget, to get all these emissions back from the atmosphere. A future carbon pricing system may not be enough in case we have net negative CO2 emissions to finance this. So we have now to build up a capital in order to have the financial means available in the future. Thank you.
Thank you, Nico. Looking if there's any other questions and comments. Yeah, one.
I would have one slightly related. In the rescue scenarios, in the no too low overshoot scenario, the emissions go down and then start going back up from 2040. What's the rationale behind that?
So it was not possible, so to say, to have a complete constant temperature or a complete constant net zero emissions scenario. This has to do with the architecture of the model. So we are first going a little below the zero line, and then we go a little above the zero line. And this is due to the constraints and the policies that we are implementing. We were playing around with the implementation, but this was, so to say, within the time frame, the best that we could achieve. So we first have, so to say, some net negative and then again some net positive emissions. And yeah, it's a difficult and complicated thing to balance this exactly. Yeah, I hope this helps to understand this particular feature of this scenario. Thanks.
Thank you, Nico. Thanks for the question. Any other questions, comments? Yes, please.
Yes, I'm curious. Thanks for the very important presentations. I'm curious to maybe hear you talk about more about how you're taking this information to the policymakers. Is that part of the project and so on? Yeah, maybe you touch on that, but yeah.
Yeah, it's a question about how we bring that question to, or like assess those questions in the policy context, and I think it's a very important one.
Now you're muted.
Sorry. Yeah, I think it's an excellent question. Should I repeat the question online, or did you get the question?
We got the question.
Okay, the question you got. Okay, excellent. So maybe just quickly to say, from the Provide project side, I mean, we've done a number of policy briefs, and we try to disseminate that as much as we can, also through our online tool. I mean, ultimately, we're still a bit in a space where the questions of overshoot are really also scientific frontiers. So I think basically the avenues of how to incorporate this into policy are challenging. But I think from these results, there are a few things that are emerging that I think also are basically things to be picked up for follow-up work. One includes the obvious consequences of what CDR should be used for. If we actually establish the need for something to be a preventive capacity, then it's like, you know, like other measures like disaster risk measures of holding water or food reserves for a disaster strike, you need to hold the capacity for CDR for such situations. So these are then clear policy implications, for example, of also if CDR and emission reductions should be actually in the same basket or should separate targets for those. And if we should set additional reduction targets or additional CDR targets for preventive measures. But then there are also other questions in the context around CDR, in particular also what are the consequences of some of the sustainability limits, but also who should pay for it. And I think Rucha has been showing, for example, a policy brief trying to do an equity assessment on the responsibilities for CDR deployment. And I think this then also kind of involves the information, not just what's physically required, what's technically possible, but also what basically the considerations of also the deliberations here at the COP, what is actually also required or in terms of incorporating questions of equity and justice. But it would be my quick response, and I'm looking to the speakers online for additional comments. Thank you.
And maybe I can just share a bit on the kind of rescue plans for the science policy dialogue. So this COP policy brief that we've presented, and also the side event, is kind of part of getting into the dialogue with different kinds of stakeholders and an international policy audience. We also had a workshop series in September to kind of have a dialogue with especially also EU DG stakeholders. We have another COP side event next year, and a policy roundtable next year in Brussels, because this is just better to kind of go to where at least EU-based policymakers are. So these are some of our plans, and we have kind of ongoing stakeholder engagement to get feedback. Like the kind of question that Dalia just asked, I think is really relevant, so that policymakers or those users of the scenario information know kind of how this kind of aligns with climate objectives. So yeah, maybe just a brief reflection from our side.
Great, thank you, Uta, and thank you for the question. If there are no further questions at this point, I want to thank you all for your attention. I want to thank you all three for joining us today. Have a great rest of your day wherever you are, and you all have a great evening here in Baku. Thank you very much.
Yeah, thanks a lot for the presentation.
Oh, back to you, Christina.
Yeah.
Apologies. No, for the last word.
Thank you
thanks
so
to the
much for
Cryosphere
all of
Pavilion.
our four speakers and to our audience. Thank you.
Yes, thank you for your attention. Bye-bye. Have a good
great
rest
time.
of the day.
Bye, thank you.
Bye.
And read the policy.